Now when a wave is entering in the plasma, there are some assumptions that has to be kept in mind. Initially we assume that there are some positive charges, some negative charges and some neutral charges in the plasma, and their density is depending upon the degree of ionization. So if we are taking about unmagnetized plasma, we are assumed that there is no magnetic field. If we consider that the plasma is magnetized, then the magnetized field is plasma is denoted by vector B, and the magnetic field of the electromagnetic wave is denoted by vector B1. Second assumption is, then we have assumed that there is no thermal agitation, so the kT should be 0. kT is equal to 0. One more assumption that we generally consider, that the ion have been fixed position and they have uniform distribution. We also assume that the plasma is infinite, so we don't take boundary condition at the behavior of plasma. The plasma is considered to be in this infinite extent, and generally we consider the electron motion occurring in the direction of x, but it can vary case to case. Now when the wave is entering in the plasma, for the sake there is no wave, we are taking only about the plasma oscillation also. We separate the equilibrium part and the perturbation part also. So we assume that equilibrium density of the electron is n0, but when there is a perturbation, then there is a distribution of density which is become Ne. So Ne has the equilibrium part and perturbation part, that is Ne is equal to n0 plus n1. Obviously n0 is much greater than n1. If V0 is equilibrium density, then the velocity of the electron at any particular moment have one equilibrium part and one perturbation part, and that becomes vector V is equal to V0 plus V1. Here we have a perturbation part and the equilibrium part, and the electric field become vector E is equal to E0 plus E1. We neglect the product of two perturbation parts in the equation. This process is known as linearization. Generally we use the process of linearization whenever we dealing with derivation of plasma. By this means the amplitude of oscillation is very small, and terms containing higher powers of the amplitude factor can be neglected, and the equilibrium quantities obviously express the state of plasma in the absence of oscillation. And then whenever we are getting product of perturbations, then the term regarding two perturbation terms we can neglect them. Also there are few things that have to be kept in mind. Because n0 is constant, so del n0 should be 0. d by dt n0 is equal to the 0. Then electrons are initially stable, so the V0 velocity should be 0. We also consider electric field E0 is also 0. Then the del n0 by del t is equal to del V. Del t is equal to del E0 over del t is equal to 0. So with these assumptions, we will try to determine the behavior of plasma when electromagnetic wave under the unmagnetized plasma. For determining the behavior of electromagnetic waves under the unmagnetized plasma, we will take help of Maxwell's equation. With these equations, we will find a dispersion relation of these waves. Here we will use Maxwell's third and fourth equation. The first equation, here we have del cross E means the curl of electric field, which is the negative of beta dot, where beta is the rate of change of magnetic field. Means this is a Faraday's law, and which says the rate of change of magnetic flux induces an EMF. Let's take the equation number 1. And another equation we will take del cross B means the curl of magnetic field, which is equals to the mu 0 d dot, where d dot and d is the electric displacement vector. Since in the vacuum the current density J should be 0, and the value of the electric displacement vector, which is equal to the epsilon naught vector E. Then the equation becomes mu 0 epsilon naught vector E dot, and the value of mu 0 epsilon naught, which is 1 over c square. After substituting the value, we get c square del cross vector B is equal to vector E dot. Let's take this equation number 2. And now take the curl of equation number 2, and with the help of vector triple cross product, we will get the c square del cross B, which is equal to the del cross E dot. And the value of del cross E, we know that minus beta. Here we have del cross E dot, then we get minus beta double dot, means the double differential of B. Where B is a magnetic field vector. And replacing the value del by ik and del by del t is equal to minus I omega. This is the value we have get from the wave equations. As you know, our wave equation n is equal to ngo e raised to power ik x minus omega t. This is the wave equation. From this equation we have the value of delta and delta d by dt. Now after substituting the value of delta and del by del t, we have c square I vector k cross ik cross vector b, which is equals to the minus of I omega whole square vector b. After that, minus c square vector k cross vector b1, which is equal to the omega b1. After solution of vector cross product, we will get minus c square vector k into vector k dot vector b minus k square vector b, which is equals to the omega dot b. And by the another Maxwell's equation, the result become c square vector k square vector b is equal to omega square b1, where k is the propagation vector, and the value we get omega square, which is equals to the k square c square, and we get omega by k, which is equal to the c, and c is the phase velocity omega by k of light waves. Then we have del cross vector b, which is equal to the mu 0 vector j plus del d by del t from the Maxwell's fourth equation. And after substituting the value of electric displacement vector d, which is equal to the epsilon naught vector e, we get mu 0 epsilon naught vector j by epsilon naught plus del e by del t. After simplifying, we get c square vector del dot vector b, which is equal to vector j by epsilon naught plus vector e dot. Let's take this equation number 5. Then taking the time derivative of this equation, we get c square del dot vector b dot equal to 1 over epsilon naught del j dot by del t plus del e double dot. Let's take this equation number 6, where double dot represents the double differential. And the curl of equation number 1, which is vector del cross vector b, we have del into del dot vector e minus del square e1, as we have earlier derived. Now we have substituted the value of vector del dot b in the equation, becomes del into del dot vector e minus del square vector e is equal to minus 1 over epsilon naught c square vector del j by del t plus double differential of vector e by c square. Let's take this equation number 8. Now replacing del by ik and del by del t by minus I omega, the equation becomes k square vector e minus I omega by epsilon naught c square vector j plus omega square by c square vector e. Here the value of vector k dot vector e perpendicular to each other as well to the direction of propagation. By transverse wave means vector k dot vector e is equal to 0. So vector k dot vector e will be 0. Then the equation becomes omega square minus k square by c square vector e is equal to minus I omega by epsilon naught c square vector j. After simplifying, the equation becomes omega square minus c square k square vector e is equal to minus omega by epsilon naught vector j. Let's take this equation number 10. Now if we consider the light waves and microwaves, these have very high frequency and the ions must be considered as fixed. Then the current density vector j, that comes entirely from the electron motion. Then the value of vector j, which is given by minus n0 e phi. Let's take this equation number 11. From the linearization electron equation, we have kT is equal to 0 And the equation of motion we have m del v by del t is equal to minus e dot vector e, where small e represents the electronic charge. And after simplifying we get minus m I omega del v by v is equal to minus e dot vector e by I m omega. Here we have substituted the value of del by del t with minus I omega. After that the equation becomes omega square minus c square k square vector e is equal to minus I omega by epsilon naught into minus n0 e v e. After that omega square minus c square k square into vector e is equal to I omega by epsilon naught n0 e into e dot e by I m omega. By simplifying we get omega square minus c square k square into vector e is equal to n0 e square dot vector e by epsilon naught m. Let's take this equation number 12. On the right hand side, n0 e square epsilon naught m is the expression for omega square p, which is the square of plasma frequency. Substituting this means omega p square, we will get n0 e square by epsilon naught m. Then we will get omega square minus c square k square dot vector e is equal to omega p square vector e. Means omega square is equal to omega p square plus c square k square. Let's take this equation number 13. This equation represents the dispersion relation of electromagnetic waves under the unmagnetized plasma. And the phase velocity of light waves in plasma is always greater than the velocity of light. As we know, the phase velocity v phi is equal to the omega by k. Squaring both sides, we get v square phi is equal to omega square over k square. From the equation of dispersion relation, we have omega square by k square is equal to c square plus omega p square by k square. So after substituting the value of omega square k square with v phi square, we get c square plus omega p square by k square is greater than c square. Let's take this equation number 14. And for group velocity, we know that Vg group velocity is equal to del omega by del k. For the finding of value of del omega by del k, we have to differentiate the dispersion relation equation. The dispersion relation equation we have omega is equal to omega p square plus c square k square. Here omega p square is constant. The differentiation of this value gets 0. And other term we will get 2 omega d omega is equal to c square 2k dk. Now after simplifying we get Vg is equal to c square k by omega is equal to c square by omega by k. The omega by k is phase velocity v phi, then we get c square by v phi. Let's take this equation number 15. After comparing both equations, we conclude that the group velocity is always less than the speed of light in plasma and the phase velocity is always greater than the speed of light in the plasma. The dispersion relation equation can be shown by with this figure. This diagram resembles that for the plasma waves, but the dispersion relation is really quite different because the asymptotic velocity, which is given by c, which is so much larger than the thermal velocity. More importantly, there is a difference in the damping of the waves. Plasma waves with larger kV are highly damped. The electromagnetic waves, other hand, become ordinary light waves, and the larger Kc are not damped by the presence of plasma in this limit. And the most laboratory plasma, the cutoff frequency lies in the microwave range.